This time we'll be looking at the naming systems of alcohols and alkenes. This will happen through a worksheet. After that, we'll be looking ever so briefly at the overarching tenets of their reactivity, alcohols and alkenes. To locate where this information is held, uh, I'm now showing you the Canvas website for lecture under the banner Weather Days, Alcohol, Alkene, Nomenclature, and some ever so brief reactivity. This is a PDF file, so that's what we'll be going through. So this sets up good enough for Weather Days to talk about nomenclature. It's rather than some more technical topic, perhaps, with their activity and curly arrows. So this is a worksheet which will begin things, and we will be uh, uh, going forward with naming alkenes and drawing them and the relation thereof. So without a bunch of you know fluff, I'm just going to head into it. So there's this name here, hexan one all. Uh, how would we draw that? So hex refers to six, okay? So I will now put to paper six carbons. I'm now drawing hexan one all. That's good. And on the first carbon out of six, see where the purple dot is? On the first carbon, I don't leave myself much room here. I will have to try again because that bond should be straight. And I'll try to piece in here an OH off of carbon one. So this is on the first carbon. For a cis carbon main chain, we have hexan one all. Shall we try hexan two all? And as you might have guessed, the hydroxyl is on the second carbon of the chain. So be it. These molecules, hexan one all and hexan two all, have different physical properties. They have different refractive indexes. They have different densities. Yeah, and also they have different chemical reactivities. Okay, so there one's a primary, one's a secondary alcohol, so there will be repercussions to come. So there is significance to these different chemicals, even though they're called constitutional isomers. And hexanthreol is instructive to draw because we can draw an OH here. Please note that alcohols can be drawn with the OH condensed or OH not condensed. In other words, I can have a hyphen bond between the O and the H. So that's the same thing. So we have to put up with that. Letter D, please. Hept 1N 3 all. So hept refers to 7. What's this N business? This refers to the start position of a double bond where a double bond starts at carbon number 1. So there will be business to attend to at carbon number 1 and 3. 1 and 3. Interesting things upcoming here. Stay tuned. So at carbon 1, I am told put a double bond starting at carbon 1, shall we? Alongside parallel park it, notch it. And carbon 3 has an alcohol. So this illustrates how nimble this nomenclature is, how you can, and in the names, kind of splice in uh, numbers to designate locations of different functional groups. So here is hept 3N1-ol, 7 carbons, smartly aligned. Here's carbon 3, business here. Here's carbon 1, business here. And at 3, I am told to start a double bond going forward. So start at 3, going, watch my finger, watch my finger, left to right, starting at 3, may pave a double bond, and at OH, at carbon 1. Here's another one to try. It is called 2-methyl hept 2N4-ol. 7-carbon chain of a kind. So 2-methyl. So far, so good. Hept 2N means double bond starts at carbon 2, pave forward 2 to 3, and carbon 4, keeping count, we have an OH. And as I said, they can be condensed or drawn out in full. So that's IUPAC. Now we see what are called common names of alcohols. So this is brought forth by alkyl alcohol. So here are some examples, not to waste any of your valuable time. Ethyl alcohol, tag on an ethyl group to an alcohol. Isopropyl alcohol. You handle this in organic chemistry 1. Little did you know it, that you were drawing these common names at the time where you were adjoining an OH namesake alcohol to isopropyl. And you remove the squiggly line connectors. If you'll forgive that bad vertex to save your valuable time. You can always check your work by counting the number of carbons. Here's isobutyl alcohol. I don't want to use your valuable time by belaboring what an isobutyl group is. So yeah, trying to be respectful of your time. So isobutyl alcohol. So yep. So that's so we have on the screen right now we have IUPAC names and also common names. Common names will persist for small alcohols. If you have a larger alcohol, it will not have a common name, such as this alcohol here, hexanthriol. It does not have a common name. It's too big. Other alcohols to bring forth, phenyl alcohol or phenol. We need a 3-membered ring, not and a 6-membered ring with 3 double bonds. I repeat, because I misspoke, a 6-membered ring with 3 double bonds, a 6-membered ring with 3 double bonds, off of which an OH. This is phenyl alcohol or phenol. Benzyl alcohol is 7 carbons strong, and it has like an elbow bend between the ring and the OH. We call it a methylene carbon. So I now uh, putting in the double bond, that's benzyl alcohol, vinyl alcohol, the letter V. Did you catch it? Make a V. Thanks. So we are doing the vinyl group, tag on an OH, and a double bond on the far side. This is vinyl alcohol, the vinyl group. Allyl alcohol. Did you catch how many L's? That there are three L's in allyl. So that's how many carbons there are in the allyl group. And on the far side, again, there's a double bond. So that's great. So these are new groups. You can add them to your collection. The allyl group, ALLYL, three L's. The phenyl group, a six-membered ring with three double bonds. The benzyl group, like phenyl, but with an elbow bend and vinyl. Draw a letter V, tag on, paste an OH and a double bond into it. I will table the amyl groups. You're welcome. And I would like to talk about ethylene glycol. So the compound ethylene is as such, and it undergoes a chemical reaction to turn it into what's called a diol. DIOL, diol. This is a vicinal diol, a, a vicinal diol. Propylene glycol. What does this invoke? Three, right? Propylene. I'm going to draw propylene and its propylene glycol across the old double bond, which is gone now. Cinch that. Cyclohexyl alcohol, a chance for you to draw a chair conformation. And usually with such chair conformations, we have the OH or any group equatorial. Better there. Okay, so let's review here. We saw it was very instructive how I arranged this lesson. It was going to be in person, but now it has to be online. Besides that, it's very instructive how we kick things off. Hexan 1-all, hexan 2-all, hexan 3-all. And you see how versatile and nimble this nomenclature method is because it allows for double bonds to be implanted into the main chains, indicated by the lettering EN. We also saw instances of simple, small molecular alkyl alcohols. We saw four different groups, which you may have seen in organic chemistry one. You may remember it has been a while. And I tabled the amyl alcohols. Here's ethylene glycol, propylene glycol. Ethylene glycol is an antifreeze. And if I can type here, these are vicinal diols. Vicinal means one atom away. So there's yet another OH, one atom away, vicinal. And diol means two alcohols. Di is two, tri is three, alcohols, plural. So with that nomenclature, before I would want to talk about any reactivity with alcohols, I would want to mention and impress upon each and every one of you that this can be a true or false question. True or false? Alcohols can do SN2 reactions like you see there. And the answer is false. Now, someone from another college can ask you this question, and by your answer, he or she can come to a conclusion about, oh, this person knows organic chemistry. Yeah. This person doesn't know their organic chemistry, so uh, so alcohols cannot do SN2 reactions. Oh, come on, why? Well, if for me to explain, it won't take me too long. I'm happy to tell you. So I'm now drawing the nucleophile, whatever it is. It doesn't matter what it is. And point in fact, it doesn't really matter what in the world it is. It's not going to work. So here it goes, trying nevertheless. And you will put in a partial positive, partial negative, but trying to save your time. So it would attack backside. The problem is you get a byproduct, this one. Recognize this from general chemistry? This is a strong base. This is drain cleaner, Drano. You pour down drains to unclog drains in plumbing in the household. This is too reactive. This will back react. So blame it. Blame it on the sodium, that's its name, sodium hydroxide byproduct. Usually byproducts are innocent and they go along their way and they leave, but not this one, not this one, not this one. This one is gonna punch back and it's gonna cause a back reaction. This one punches back. And again, just to go to show you that alcohols can be presented with the OH condensed or the OH bond drawn out. So it doesn't matter. That doesn't matter. You will see both. You will see both the both condensed stands. So there's not enough room to show everything. So this is where the partial positive would be. Carbon is less electronegative, oxygen's more electronegative. So I mean, another way of saying this is chloride. Fluoride is a leaving group. Chloride is a leaving group. Bromide is a leaving group. It goes on its happy way. And but these are all leaving groups. Hydroxide, I drew it like that because the negative charge is on the oxygen. Or you can draw it like this, not OH minus. This is terrible because you're telling your audience that the negative charge is on hydrogen and it's not. This is bad form. It's lazy in terms of presenting structures. It's inaccurate. So hydroxide is is not a leaving group. Is not a leaving group. LG stands for leaving group. So the reason has to do with the byproduct. So I reiterate, what this is going to do is zoom, go right back and punch back and cause a back reaction. As soon as it forms, it's going to go back because hydroxide is just too reactive to just sit there and do nothing. Do you know if you had a round bomb flask of sodium hydroxide that the round bomb flask glass will get thinner and thinner and thinner and thinner until it's paper thin and the glass breaks. That's how reactive hydroxide is. It eats glass. It dissolves glass. So if hydroxide dissolves glass, then don't you believe that then this is going to back react. So alcohols cannot do SN2 reactions. It's good that we know that. That way, if we're asked that question on the street, we can act like we know our organic chemistry. And proceeding along, now let's talk about the nomenclature of alkenes, shall we? Thank you. So, hept-1-ene. Respectful of your time as ever. I'm getting right to it rather than giving you 3 minutes worth of fluff or background. So, hept-1-ene, like that. Hept-4-ene, 7, carbon 1, carbon 2, carbon 3, carbon 4. Forgive me, but I feel I should do that for at least one of these examples. And carbon 4, make a double bond. I'll live with that. Uh, make a double bond from carbon 4, oct-3-ene. And here's their third carbon, right? And at carbon 3, going from left to right, like you would read a magazine or a book, you want to place a double bond there. I'll live with that. Next line, please. Cyclopent-1-ene. Cyclopentane. I'll live with that. Cyclopent-1-ene. Usually it's just called cyclopentene. It's inferred that the double bond is at carbon 1. Uh, oh, look, I got myself going there. I thought this was cyclone. It's not. So I'll begin again. When you do this, why don't we start here? Okay, pent-2-ene. Here's pent-2-ene, carbon 2, make a double bond. Thank you. At carbon 2, we also want to put a methyl. And carbon 3, we want to put an ethyl, which uh, that'll be nice. So we have that. Here we have again, we're going to start here oct-2-ene. So thankfully I have enough paper off to the right here. I'll live with that. Oct-2-ene. And 4-N-butyl. You're saying to yourself, well, how come this isn't the main chain here? That's more carbons in it. There's 9. That beats 8. Well, the main chain has to include the double bond because it's that important with respect to reactivity. Okay, so that let me just type this here. Uh, the main chain has to include a double bond at the expense of a longer main chain. Sorry. So here's maybe you remember ethylene from the previous page. Ethylene is common name, alkaline. Oh, uh, business here. Oh, ethylene. It also could be called, if you wanted to, ethane. Oh, no, it can't. There's a double bond in there. Ethene. Thank you. Change the suffix to "ene" to indicate a double bond. Eth-1-ene. You will never see it called eth-1-ene. Eth-1-ene. It's always called ethylene. Here's propylene. By the way, someone in the departments, their dog is named Ethel, which I think is a really neat name for a dog. Every time I see Ethel now, I always think of the dog. Propylene, propane, right? Propane, 3 carbons, and have one of them be a double bond. So there's two ways to draw propylene. Styrene is a double bond off of a six-membered ring. Follow along if you will, with three double bonds in the ring itself. Call it aromatic. So it's a vinyl aromatic. Methyl vinyl ketone. Give an acronym MVK. Here's a carbonyl. Here's your carbonyl with the methyl. You could do this all in one fell swoop if you want. I was just taking it a piece at a time. There was a song Johnny Cash wrote called I Got It One Piece at a Time. It's a good song. Vinyl. And the vinyl group is like that. Let me just make a little bit better of a vertex. Oh boy, I missed that one. Not too late to try again. I'm trying to draw a vinyl group off of this. So, all right, I'll live with that. Butadiene, or else buta 1,3-diene. So there's going to be a double bond starting at carbon one. Uh-huh. And there's going to be a double bond starting at carbon three. Uh-huh. So draw butane. Here's the double bond starting at carbon one. And here's a double bond starting at carbon three. Again, you can do this all at once if you wanted. Cinch it. I'll drew another one up here. Double bond starting at carbon one of a four carbon chain, double bond starting at carbon three of a four carbon chain. We have it. Remember the vinyl group? Vinyl amine. An amine is NH2. Vinyl. Remember how we did that? Vinyl, right? I'll type the word vinyl. It begins with letter B. That's your hint. Draw a V. Draw a V. Terrific. Double bond on one side, and whatever group you're putting up with is on the other side. NH2 is amine. Allyl ether. Remember the hint? Three L's. That means hint, hint, draw three carbons. I'm going to skip allyl ether. Okay. I'm going to skip that. I don't want to give too much information. And yeah, and to draw an ether, like that's we have alcohol and alkene and add in our ether. So I'll table that. Okay. So thank you. But we can nevertheless do oct 1, comma 4, comma 6 triene. Here's oct, ane, that is. And we have a double bond starting at carbon 1. We'll have a double bond starting at carbon 4 and a double bond starting at carbon 6. Starting at carbon 4, starting at carbon 6. This is called a triene, three alkenes. Tri is the three, alkene is the double bond, three double bonds. Here we have a chance for you to draw. I mean, if you want to put me on pause, do so and give yourself a chance to draw hex 2, comma 5 diene. So I would recommend put me on pause and see if you get what I get. Okay, hopefully you got that. An isoprene unit is important to biochemical concerns. It is butadiene with a methyl on it. This is called an isoprene unit, and this is the precursor used to make cholesterol in the body, isoprene. And methylene cyclohexane is a strange looking molecule because you have a double bond external to the ring. It's called an exocyclic double bond. Can add that. It's a footnote. Exocyclic, that means outside the ring. Double bond. Back up above, this with cyclopentoine was an endocyclic double bond. Endo means double bond was inside the ring, not outside. There are endocyclic double bonds and there are exocyclic double bonds when it comes to rings. Endocyclic and exocyclic. Endocyclic and exocyclic. So we've seen how IUPAC names persist to a greater extent in alkenes. That is to say, otherwise stated, there aren't that many common names for alkenes. Here's some: ethylene, propylene. That's about it. Really, there's isoprene. Yeah, and we saw also instances of how to draw trienes and dienes. Good for us. I think I'll cover this at another time. So that's just let this sink in. Good. That's too much information overload. But you can see how important information is, especially for physician assistants majors, double bonds in animals, double bonds in plants. So you can see that I hope you would want to know that information. I hope you're thirsty for that information. So here's something we can do, which is helpful. So, and we're going to be marking V for vinyl positions, B for benzyl positions, P for phenyl positions, and A for allyl positions. So vinyl is resting plunk on a double bond. Oh, sorry, I thought I could do, I think I can. So I just have to type it again. So let allyl is one position away from my double bond. So we'll mark the allyls all at once. Batting third. Oops. Phenyl is on a six-membered ring with three double bonds. Find one of those on a piece of paper to look at A. So this sounds bad right now, but I don't think it is. So hang in there. We're just getting to definitions. And finally, benzyl. I think you heard about that before, right? You want to do orange with this one? Benzyl is one position away from a six-membered ring with three double bonds. We call those rings aromatic, by the way, if you want a niftier name for that. So now that we have the coding correct, let's you and I work through these and let's go on the hunt for vinyl groups. Okay, let's you and I hunt for vinyl groups. We're on the hunt for vinyl groups. Here's one of a vinyl position. Little V here, little V here. Vertexes, which have double bonds on them. There's some more vinyl positions. A vinyl position, a vinyl position. Ah, good. Ah, good. Shall we proceed? Some more double bond, vinyl at a double bond, vinyl at on a double bond. These are all vinyl positions. Here's another vinyl position. So we did that much and fit it on the screen. Okay. All right, so allyl, I'm changing color to red. Fun, isn't it? So allyl is one away from vinyl. So here's allyl. I don't know if you make your A's like this or like that, but I'll make my A's like this if you will permit me. Allyl. Allyl's one away. Here's allyl one away. Allyl one away from vinyl. Allyl one away from vinyl. These are all allyl positions. And that allyl position has a certain something for chemical reactions. So there's something special about an allyl position. It can do chemical reactions. Look out for the allyl position. So in here, if there's not an A on it and there's not a V on it, it's not reactive. So that's like Vaseline. It's not reactive. Now here's some more allyl positions. One away from a double bond, one away from a double bond, one away from a double bond. And would you look at this, in this molecule D, there's only one carbon which is not reactive. It's the carbon without a letter V and without a letter A. Allyl one away, allyl one away. So changing pen colors to purple, because here come the phenyl positions. This time I'm going to label purple P's on, it has to be a six-membered ring. If it's a seven-membered ring, you're supposed to use the V's, the green V's. This is a six-membered ring. You'll see end of April how these six-membered rings are called aromatic. It used to mean aroma or smell, good or bad. Now it means reactivity of a certain type. So again, we have a six-membered ring, and we have to go all the way around and label each of these P's, their phenyl positions. They have a certain something with their activity, a certain something with their activity to be aware of. And the benzyl positions, here comes orange for benzyl. Benzyl is one away from a ring. There's a handsome looking letter B there. Here's another sharp looking B. And that's it. Two benzyl positions. So this was nicely delivered on a computer for you. And vinyl is on a double bond. A picture's worth 1,000 words. I know you were chomping at the bit to see this played out rather than suffering through definition talk. Allyl is one away from a double bond. Likewise, benzyl is one away from a six-membered ring with three double bonds, aromatic. And phenyl is the six-membered ring, not not a heptagon, not one of those clumsy-looking heptagons, not a pentagon, a hexagon with how many? Three double bonds. That would qualify as phenyl. It's pretty specific. It's pretty specific. And there's some more you can try. If you like, you can turn in G, H, and I for bonus 1 week from the assignment of this online lesson. Okay. Mm, uh-huh. So G, H, and I are bonus for lecture, as well as J, K, L, and M. Use your critical thinking there, okay? Use your critical thinking. You've been empowered with how to determine those. You've been empowered. So G, H, I, J, K, L, M are gifted as bonus. A little Easter egg for listening to this lesson. Thank you. Just a little bit more to go about reactivity, perhaps. If I can find out how to switch this. I think this does it. Okay. Just let me have 10 seconds to draw. This is the ion of acidity, and this is the ion of basicity. You almost made it through this lesson. Another video lesson. Okay, so this is an alkene with an overhead view and alkene with an edge-on view. Oh, wrong one. I'd like to show you mole view. Please note how double bonds are flat. Okay, so you see the flatness of the double bond. Double bond is flat here. Don't take my word for it. Look at the hydrogens in white. That's a double bond and they're flat. Compared to the sp3, and here's an alcohol. Please believe that for this alcohol here, there's a how can I do this here? There's a lone pair in front and there's a lone pair in the back. So the oxygen atom is sp3 tetrahedral, as are all the gray carbons up until the double bond, which is flat. So it goes tetrahedral, 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 three-dimensional, 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 tetrahedral, three-dimensional, tetrahedral, three-dimensional, triple planar flat, double bond flat, tetrahedral, three-dimensional, front, back, left, right, up, down. So that's some juice to support the substantiation that this is a flat molecule. So we have, when we're looking at, as this lesson winds down, uh, a double bond, remember, is composed of sigma overlap plus pi overlap, constituting three overlaps. This is sigma overlap. You probably already know this, don't you? Whereas I'm fumbling around trying to get this to work here. So, uh, what to do? It was going so well, wasn't it? There's pi overlap. You already know that, don't you? You didn't need me to belabor it. And here's sigma overlap. How about red? Yeah, there's sigma overlap. Uh, and as was harped upon, an alkene is electron rich. Because a double bond has four electrons in it. A single bond has two electrons in it. A double bond has four electrons in it. So they are electron rich. As such, it is stated that alkenes are Lewis bases. Another word for that, it begins with N. Nucleophile, attackers. A Lewis base, a nucleophile, and an attacker. I think I stole my thunder from the next row. Is a nucleophile. Oops. So the last question I have for you is as I was going to try to deliver it, and then we'll close this lesson down, is here's hydroxide. The thing that we blamed for alcohols not being able to do SN2 reactions. We put the blame on it. And here's the ion of acidity and the ion of basicity. Will an alkene react with H plus, or will an alkene react with HO minus? I'd like to get you to understand that an alkene will react with, drum roll, H plus, because aren't there four electrons here as I'm drawing them out? Don't electrons have negative charges? This is electron rich. Doesn't a north pole attract a south pole with magnets? Likewise, won't a negative charge attract a positive charge? Oh, yeah. Whereas this is halted repulsion. Stop. Halt. Repulsion. So that's how a lot of reactions kick off. We have alkenes reacting with H plus, and we get carbocations. So I will find out how long this lesson was when I end the movie. We are now done, and we have learned alcohol IUPAC nomenclature. We have learned alcohol common name nomenclature. We have seen alcohols cannot do SN2 reactions. Why? Because the byproduct is Drano, and it's going to punch back. It'll back react. Hydroxide, if you get some on your fingertips, doesn't it feel greasy? That's your skin turning into soap. That's how reactive hydroxide is. And no wonder alcohols giving hydroxide byproducts for SN2 cannot complete their SN2 reaction. It back reacts, it spins back. We talked about alkene nomenclature, how that splicing of the number predicts the position of the double bond. We talked about alkene IUPAC, that was IUPAC and alkene common name nomenclature. We talked about the vinyl, benzyl, allyl, and phenyl positions. I gave you a gift bonus and an Easter egg for watching. Wow, interesting, isn't it? So it'll be interesting to see how many come in, how many of those bonuses come in. And we also have the reasons why alkenes are reactive because they're electron rich. There's one, two, three, four electrons, four electron rich, and we saw how an electron with a negative charge will attract to a positive charge. So alkenes will react with H plus rather than repulsion. Repulsion, alkene, 4 electrons, hydroxide, 6 dots. Oh boy, that's repulsion there. And they're called nucleophiles. So we will close this down, and in so doing, thank you for watching and taking investment in your learning for organic chemistry, which will pay off handsomely. You'll see in the future across all your science courses. A good day to all, or a good evening. Bye.